This lecture is about the probabilistic latent semantic analysis, or PLSA. In this lecture, we're going to introduce probabilistic latent semantic analysis, often called the PLSA. This is the most basic topic model, also one of the most useful topic models. Now, this kind of models can in general be used to mine multiple topics from text documents. And PLSA is one of the most basic topic models for doing this. So let's first examine this problem in a little bit more detail. Here I show a sample article, which is a blog article about Hurricane Katrina. And I showed some sample topics. For example, government response, flooding of the city in New Orleans, donation, and the background. You can see in the article we use words from all these distributions. So we first, for example, see there's a criticism of government response, and this is followed by the discussion of flooding of the city and donation, etc. We also see background words are mixed with them. Right? So the goal of topic analysis here is to try to decode these topics behind the text, to segment the topics, to figure out which words are from which distribution, and to figure out first what are these topics. So how do we know there's a topic about government response? There's a topic about the flooding of the city. So these are the tasks of a topic model. If we can discover these topics, can color these words as you see here to separate the different topics, then you can do a lot of things, such as summarization or segmentation of topics, clustering of sentences, etc. So the formal definition of the problem of mining multiple topics from text is shown here, and this is actually a slide that you have seen in an earlier lecture. So the input is the collection, the number of topics, and the vocabulary set, and of course the text data, right? And then the output is of two kinds. One is the topic category characterization, theta i's. Each theta I is a word distribution. And second, it's the topic coverage for each document. These are pi sub ij's. And they tell us which document covers which topic to what extent. So we hope to generate these as output, because there are many useful applications if we can do that. So the idea of PLSA is actually very similar to the two-component mixture model that we have already introduced. The only difference is that we're going to have more than two topics. Otherwise, it's essentially the same. So here I illustrate how we can generate the text data with multiple topics. And naturally, in all cases of probabilistic modeling, we would want to figure out the likelihood function. So we will also ask the question, what's the probability of observing a word W from such a mixture model? Now, if you look at this picture and compare this with the picture that you have seen earlier, you will see the only difference is that we have added more topics here. So before we have just one topic besides the background topic, but now we have more topics. Specifically, we have K topics now. All these are topics that we assume that exist in the text data. So the consequence is that our switch for choosing a topic now is multi-way switch. Before it's just a two-way switch. We can think of that as flipping a coin. But now we have multiple ways. First, we can flip a coin to decide whether we will talk about the background. So it's the background lambda sub b versus non-background. So this 1 minus lambda sub b gives us the probability of actually choosing a topic, a non-background topic. After we have made this decision, we have to make another decision to choose one of these k distributions. So there's a k-way switch here, and this is characterized by the pi's, and they sum to 1. Right, so this is just the different design of switches, a little bit more complicated. But once we decide which distribution to use, the rest is the same. We're going to just generate the word by using one of these distributions, as shown here. Okay, so now let's look at the question about the likelihood. So what's the probability of observing a word from such a distribution? What do you think? Now, we've seen this problem many times now, and if you can recall, it's generally a sum over all the different possibilities of generating the word. So let's first look at how the word can be generated from the background model. Well, the probability that the word is generated from the background model is lambda multiplied by the probability of the word from the background model, right? Two things must happen. First, we have to have chosen the background model, and that's probability of lambda sub b. And then the second, we must have actually obtained the word w from the background, and that's probability of w given theta sub b. Okay, so similarly, we can figure out the probability of observing the word from another topic, like a topic theta sub k. Now note that here's a product of three terms, and that's because the choice of topic theta sub k only happens if two things happen. One is we decide not to talk about background, so that's probability 1 minus lambda sub b. Second, we also have to actually choose theta sub k among these k topics, so that's probability of theta sub k, or pi. And similarly, the probability of generating the word from the second topic and the first topic are like what you are seeing here. And then so in the end, the probability of observing the word is just a sum of all these cases. And I have to stress again, this is a very important formula to know, because this is really key to understanding all the topic models, and indeed a lot of mixture models. So make sure that you really understand the probability of W is indeed the sum of these terms. So next, once we have the likelihood function, we would be interested in knowing the parameters, right? So to estimate the parameters. But first, let's put all these together to have the complete likelihood function for PLSA. Now the first line shows the probability of a word as illustrated on the previous slide. And this is an important formula, as I said. And so let's take a closer look at this. This actually contains all the important parameters. So first we see lambda sub b here. This represents the percentage of background words that we believe exist in the text data. And this can be a known value that we set empirically. Second, we see the background language model, and typically we also assume this is known. We can use a large collection of text, or use all the text data we have available to estimate the word distribution. Now next, in the rest of this formula, excuse me, you see two interesting kinds of parameters. Those are the most important parameters that we are after. So one is pi's, and these are the coverage of topic in the document. And the other is the word distributions that characterize all the topics. So the next line then is simply to plug this in to calculate the probability of a document. This is again of the familiar form where you have a sum and you have a count of a word in the document and then log of a probability. Now it's a little bit more complicated than the two component, because now we have more components, so the sum involves more terms. And then this line is just the likelihood for the whole collection, and it's very similar, just accounting for more documents in the collection. So what are the unknown parameters? I already said there are two kinds. One is coverage, one is the word distributions. And again, it's a useful exercise for you to figure out exactly how many parameters there are here. How many unknown parameters are there? Now, trying to figure out that question would help you understand the model in more detail. And it would also allow you to understand what would be the output that we generate when we use PLSA to analyze text data. And these are precisely the unknown parameters. So after we have obtained the likelihood function shown here, the next is to worry about the parameter estimation. And we can do the usual thing, maximum likelihood estimate. So again, it's a constraint optimization problem, like what we have seen before, only that we have a collection of text and we have more parameters to estimate. And we still have two constraints, two kinds of constraints. One is the word distributions. All the words must have probabilities that sum to 1 for one distribution. The other is the topic coverage distribution. And a document will have to cover precisely these k topics So the probability of covering each topic would have to sum to 1. So at this point, it's basically a well-defined applied math problem. You just need to figure out the solutions to an optimization problem. There's a function with many variables, and we need to just figure out the values of these variables to make the function reach its maximum.